In this lesson, we're going to look at Lewis structures. Remember that the electrons that are involved in bonding are the valence electrons. And so we need a model, we needed a model to represent the simple sharing of electrons between atoms in a covalent bond. So a scientist by the name of Gilbert Lewis suggested the simple model way of showing the valence electrons in an atom. Uh, he proposed electron dot structures. Now, the electron dot structures were for representing the electrons within the atom themselves. They consist of this chemical symbol with the element plus the dots for each valence electron. So, for just a simple electron dot structure, just for an atom, for hydrogen, for example, since he has one valence electron, you would draw H with a single dot there. If it were helium, he has two valence electrons, so you would represent his dot structure He with two dots. Remember, hydrogen and helium follow the duet rule. And then for an atom like, for example, oxygen, he's in group 6A, so oxygen would have six valence electrons, so you would put 1, 2, 3, 4, 5, 6. Six dots around. So he suggested that simple model, if you will, to represent the valence electrons around atoms. Now, we also use these dots to represent bonding electrons in molecular compounds. So we use dots to represent non-bonding electrons and dashes to represent bonding electrons. And when you're drawing Lewis structures, you are only going to be showing your valence electrons. Now, I know that you've already got this is a review for you, so you've already gotten most of this part copied down. So I'm going to just kind of rush through these this first part of the notes, and we'll go back and explain the examples in the details here, and then we'll do some more guided practice together. So the basic rules for how to draw or to write a Lewis structure is you want to add up your valence electrons for all atoms in the compound. So you're going to sum them up, remembering that you can easily determine your valence electrons by referring to the group number on the periodic table. Now, if it's a polyatomic ion that you're drawing, remember that you're going to add one electron for each negative charge. And if it's a polyatomic cation, you're going to subtract one electron for each positive charge. Now, the central atom is always going to be the atom that is the least electronegative element that isn't hydrogen, because hydrogen can never be in the middle. Central atom, Ca, refers to the element in the middle of the structure, and that will never be hydrogen. But the way you can determine which atom should go in the middle is it will be the least electronegative element. You're going to connect the outer atoms to the central atom. Always start with single bonds, and those are the dashed lines that you see here, making sure to keep track of your electrons. So when you initially add up your valence electrons with PCl3, we see that phosphorus has 5 valence electrons, and there's 3 chlorines, and they have 7 valence electrons apiece. So that's going to give you 5 plus 21, which gave us a total of 26 total electrons. So when you first connect your chlorines to the phosphorus with your dashes, you have used 2, 4, 6 electrons, because every single dash bond represents a shared pair of electrons, so it's 2, 4, 6 electrons. So as you keep track of your electrons, your total electrons minus your bonding electrons, 26 minus 6 will leave you with 20. And these are going to be our dots that we're going to place around to try to fulfill the octet rule. You're going to then fill the octet, so the outer atoms, except for hydrogen, remember he follows the duet rule, but hydrogen is not in this example. So we said we had 20 dots. So you're going to put 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, now that I have filled all of those, I made sure that all the chlorines have their octet. I still have 2 electrons remaining, so they're going to end up going on the phosphorus to fulfill his octet. That's going to give every atom 8 electrons, 8 around the chlorines, that's their octet, and phosphorus has 2, 4, 6, 8. So that is your correct Lewis structure for PCl3. The octet rule will need to be satisfied. Now, if you happen to run out of electrons before the central atom has its octet, that's when you're going to start forming multiple bonds until you do have an octet of electrons around every element present. Now, I do want you to remember there are certain elements that will always follow the octet rule, and that is fluorine, oxygen, nitrogen, and carbon. There's never going to be an exception to the octet rule with them. So I just remember it spells FONC. FONC, if you wanted to kind of have a way to remember it. So we see the multiple bonds having to be formed here in a molecule of HCN. So if you were to look at your Lewis structure, well, excuse me, your molecule formula HCN and add up your valence electrons, hydrogen has 1, carbon has 4, and then nitrogen has 5. So that's going to give you a total of 10 valence electrons that are going to be used in bonding. So when you connect everything to the central atom, carbon being the central atom, with a dashed line, single bond to the hydrogen and a single bond to the nitrogen. And we've used 4 electrons. So you would say 10 minus 4, and that will leave you with 6 electrons you still need to place. Now remember, hydrogen follows the duet rule. So hydrogen is satisfied already. You will never put dots on hydrogen. So we're going to arrange the remaining electrons around the nitrogen. So you put 2, 4, 6, and that will use up all of the electrons that we had. So here's where it says if you run out. So we've run out of electrons here before the central atom has its octet. Notice nitrogen has its octet, 2, 4, 6, 8. Hydrogen has its duet, 2, but carbon only has 2, 4. So this is when you would need to form multiple bonds. Carbon needs 8 electrons. Carbon only has 4. So nitrogen has some he could loan him. These are called lone pair electrons. And so nitrogen is going to swing a pair down and swing a pair up. So these are going to swing up and down, as you see here. And that leaves you with your final structure like the one we see here. Triple bond between the carbon and nitrogen. With the lone pair on the nitrogen, nitrogen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8, and hydrogen has 2. So the correct Lewis structure for HCN is represented here. Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. Remember, they're trying to strive for stability. And the way that they get stable is to get that octet or that full valence shell. Now, except for hydrogen and helium, because they only have an s orbital. And remember, the s orbital is full when it gets 2 electrons in it. An octet of electrons consists of a full s and a full p subshell in an atom. There are many exceptions to the octet rule, but this does provide us a useful framework for many important concepts in bonding. So let's look at some of the exceptions to the octet rule. Well, boron and beryllium happen to be 2 elements that tend to be satisfied with less than 8. We call them electron deficient. And that is because they have very low electronegativities. Remember, electronegativity is like that pull or a tug of war that the atoms have with the electrons. So they're fighting or they're vying for ownership of the electrons. Well, boron and beryllium have very low electronegativities, and they're simply not strong enough to pull any electrons over. And for that very reason, that is why many compounds that contain boron and beryllium are very, very unstable and reactive due to this instability. Now, another exception, set of exceptions that you want to remember is that elements in the 3rd period and beyond, they tend to exceed the octet rule. Okay, they have what we call an expanded octet. Why? Well, it's because they have empty d orbitals. So when you think in terms of the s orbital, the p orbital, and the d orbitals, and we could go as far as the f orbitals, but they're not; those electrons are not going to be involved in bonding. Remember, we learned about the s orbital. We said you have one orientation, and it can hold 2 electrons. So we could put the electrons in up, down. That will be your s orbital. So an s orbital, if it is full, can only hold 2 electrons. So 1, 2. And then we learned that a p orbital has 3 subshells. So if you're filling in your electrons in your p orbital, remember the 3 subshells for the p, 2 electrons per subshell. It can only hold 6 electrons. So you would go like up, 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 and then down, down, down. So there's 2 in the S and 6 in the P. And 2 plus 6 gives you your 8, your octet of electrons, which is what most atoms tend to do. But when you get in the 3rd period, remember the d orbitals, That's where they come into your electron configuration. So if you're writing your electron configurations, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So the d orbitals are introduced in the third energy level. So I want you to think of those d orbitals. Remember, there were 5 subshells for the d orbital. And for the d orbitals, they have 5 subshells. So that's like having a total of 5 empty rooms in a house. And if you were to think about it, if you had a house large enough to have 5 empty rooms, you could accommodate guests very easily. Those electrons are like the guest that come to visit in your and sleep over in your empty rooms. So if you have an element that is in the third period or beyond, those d orbitals are sitting there unoccupied, like empty rooms in a very large house. So this is why it can accommodate extra electrons, because they have those empty d orbitals. They're empty, there's nothing there. So it's like an empty room in a house. Those are the orbitals that can hold those extra electrons. And this happens with elements in the third period or beyond. And this is what we call this is called an expanded octet. So we're going to switch over and we're going to take a look at these 8 examples, and we're going to draw the Lewis structures for each of these. Now we're not going to talk about the actual Vesper shapes yet. We're just going to practice drawing the structures, and in another lesson we will be looking at the actual geometry of the molecule. But in your notes, we have 8 molecules that we're going to draw. So let me pull that up. You already have this. Okay, you should have your periodic table out. And so let's start with CH4. This is our first example. So let's add up our valence electrons. Again, have your periodic table out so that you can follow along. Carbon is in group 4A, so it has 4 valence electrons. There's 4 hydrogens, and they have 1 valence electron apiece. So that's going to give you a total of 8 valence electrons. Now, anytime during the video, if you need to pause it and kind of do your own, go ahead and do that, and then maybe resume it, just to make sure that you know how to do these without having to rely on myself guiding you through it. Review over this anytime. If you need to back it up and rewatch it, do that so. But make sure that you are looking at your periodic table and following along. So carbon is going to go in the center, and you're going to put 4 hydrogens on it with single bonds. So always start with single bonds. So I'm going to pretend the carbon is in a square box having 4 sides. So 4 single bonds, and now let's attach our hydrogens. Now remember, the hydrogen follows the duet rule, which means hydrogen is always satisfied once it gets 2 electrons. So I put 2, 4, 6, 8 electrons out. So 8 minus 8 means I have no electrons left. And luckily, carbon already has his octet. Hydrogen has his duet, so you're finished. So that is the Lewis structure for methane. Let's look at another molecule containing carbon. So again, carbon has 4 valence electrons. There's 4 fluorines, and he's in group 7A, so there's 7 valence electrons apiece. That's going to give you a total of 4 plus 28, which gives you a total of 32 electrons. So these atoms have 32 total valence electrons that they're going to use to bond with. So let's put our central atom down first, which is our carbon, and there's 4 fluorines to attach. Again, single bonds to start off with, and you're going to sort of pretend that the carbon is in a square, so you got a top, bottom, a left, and a right. Now, we have used 2, 4, 6, 8 electrons, so let's subtract 32 minus 8, and that's going to give you a total of 24 electrons. Okay? So now, carbon already has its octet, so we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that finishes off the remaining electrons that we had. We've made sure that everybody has their octet. I had exactly enough electrons to satisfy the octet rule for every element present. All right, let's take a look at a polyatomic ion. So here we have NO with a +1 charge. So we have 5 valence electrons for nitrogen, because he's in group 5A. Oxygen's in group 6A, so he has 6. And that positive 1 charge means it's lost 1 electron, so say -1. It's lost 1 electron. That's going to give us a total of 10 electrons. All right, so now we're going to connect. We don't have a central atom here, so we're just going to connect the nitrogen to the oxygen in a straight line. All right, we've used 2 electrons, so say -2. That means I have 8 electrons that I still need to use. So let's place those electrons. 2, 4, 6, 8. I've used up all of my electrons. Now notice what happens here. You got to go back and check for the octet rule and make sure it is satisfied. So nitrogen, he's pretty happy. He's got 2, 4, 6, 8 around him. But let's look at the oxygen. 4. So you're not finished yet because not every element has its octet. And so since nitrogen has some lone pairs he could potentially lone, oxygen's pulling with all of its electronegativity that he has. So he's going to manage to pull 2 electrons from the top here, and he's going to have to pull 2 more because he needs a total of 4. And so when you do that, you want to redraw your final structure. Your final valid structure should have the nitrogen with a triple bond between that and the oxygen, because oxygen pulled a pair down and a pair up, and that left 2 electrons on the nitrogen that were lone pairs, and oxygen had his 2 lone pairs as well. Now don't forget, if it is a polyatomic ion, you do draw the Lewis structure in brackets and you indicate the charge as a superscript. So this is the Lewis structure for nitrogen for NO+. All right, let's take a look at BF3. So here we have boron in group 3A. He has 3 valence electrons. There's 3 fluorines. They have 7 apiece. So that's going to give you 3 plus 21, which gives you a total of 24 electrons that we have here to use for bonding. So we're going to put our boron down, and we're going to place our 3 fluorines around the boron. Okay. So I've used 2, 4, 6 electrons, so subtract 6, and that's going to leave you with a total of 18 electrons. So we're going to place those electrons starting with your outer atoms first. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. So you run out of electrons here, and you want to check to see if the octet rule has been satisfied for your elements. Now, remember something special about boron. Boron is very weak in his electronegativity. So boron's electronegativity is 2.0. Fluorine's electronegativity is 4.0. So fluorine is twice as strong as boron. So what you've got going on here is you've got 3 fluorines pulling on boron. And so remember we said that boron and beryllium tend to be electron deficient. Boron is too weak in his electronegativity to manage to swing any from the fluorines because they're just too strong and they overpower it. So this is the actual Lewis structure for boron trifluoride. Because boron is the exception, we have to leave him with with only 6 electrons. He is simply not strong enough to pull the electrons that he needs, that he desires. All right, let's look at number 5. So sulfur is in group 6A. He has 6 valence electrons. There's 6 fluorines, and they've got 7 valence electrons apiece. So that's going to give you 6 plus 42, and that gives us a total of 48 electrons. Okay, so this is going to be one of these expanded octets, which is okay because let's look at who we're dealing with here. We're dealing with sulfur. So remember we said elements in the 3rd period and beyond. And if you find sulfur, he is in the 3rd period. So even though sulfur doesn't have the d orbitals holding electrons, those d orbitals are there. They're just empty. So it's like the house is full of those orbitals, full of those subshells. There's just no electrons there. So since he's in the 3rd period, they have empty d orbitals. So this element, sulfur, is going to be able to accommodate extra electrons if it needs to. So let's draw the structure. We have 6 fluorine. So this is going to be an expanded octet. You got to put every element on the central atom. So we're going to put 1, 2, 3, 4, 5, 6. Now we're going to talk about on another day, actually next week, we're going to talk about well, actually it'll be this week that we're talking about it. What this would look like. And hopefully you read in your book a little bit about it when you did your vocabulary, but this is This particular structure is called octahedral. That's what we will learn. And it's a 3D molecule. So we have the axial position, which is up and down, the axis. And then this, what looks like, I guess, whiskers on the side, this is actually like a skirt, and it's three-dimensional. So it's really like a tutu around a ballerina's waist, if you want to think of it that way. And we're going to look at our models and in our next class, and you'll kind of see the 3D model and what it looks like. But you have your axial position and your equatorial position. But you have 6 fluorines, so we've attached all 6 fluorines to the central atom. So we're going to put fluorine on the top, fluorine on the bottom, and then all 4 fluorines on the equatorial position as well. All right, so now we've used 2, 4, 6, 8, 10, 12 electrons. So let's subtract 48 minus 12. And so that's going to give us 36 electrons that we're going to use. Okay, so now let's check out the, put the electrons around the fluorines. So every fluorine needs 6 more apiece. So there's 6, 12, 18, 24, 32, 36. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Those are all 36 electrons. All the fluorines have their octet, and the sulfur actually has an expanded octet, which is okay because he is beyond the 3rd period. All right, let's look at PCl5. Phosphorus is in group 5A. So he has 5 valence electrons. There are 5 chlorines, and they have 7 valence electrons apiece. So that's going to give me 5 plus 35, which is a total of 40 electrons. All right, so we're going to put our phosphorus down first, and we have 5 chlorines to attach to the phosphorus. So again, look where phosphorus is located. He's also in the 3rd period, so any element in the 3rd period and beyond is going to be able to accommodate those extra electrons if it needs to. So I'm going to do my axial position, up, down, and then I always do the equatorial position. So you have 2 there and 1 there. Okay. Now, I'm going to connect your chlorines. You got 5 chlorines to draw on the structure. We've used 2, 4, 6, 8, 10 electrons, so 40 minus 10, and that's going to leave me with a total of 30 lone pairs that I have to use. So let's start around and let's place our 30 lone pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So we run out of electrons, and all the chlorines have their octet. That is your Lewis structure. All right, now we have H2SO4. Now this is an oxyacid, and what you want to remember with oxyacids is that your hydrogens always go on an oxygen. So with an oxyacid, the hydrogens always go on an oxygen. You have 2 hydrogens, and they have 1 valence electron apiece. You have 1 sulfur, and it's in group 6A, so it has 6 valence electrons. You have 4 oxygens, and it is in group 6A, so it has 6 valence electrons also. So we get 2 plus 6 plus 24, and that's going to give me a total of 32 electrons that we are using here. 32 electrons. So we're going to put our sulfur down, and we're going to connect the 4 oxygens to the sulfur. 1, 2, 3, 4. Now, you might be tempted to put your hydrogens on the sulfur too, because technically sulfur can accommodate those extra electrons. However, anytime it's an oxyacid, acids always have their hydrogen on an oxygen. That is very important to remember. Oxyacids, you might want to write it down, always put the hydrogens on an oxygen. So now I'm going to put 2 hydrogens. I'm going to kind of distribute them around so it's evenly spaced. So I'm going to put 1 hydrogen here, and I'm going to put 1 hydrogen here. It really does not matter which oxygen you put it on as long as you don't put them on the same oxygen. All right, let's add up our electrons that we've used. 2, 4, 6, 8, 10, 12. So minus 12, 32 minus 12 is going to give me a total of 20 electrons that I still need to use. Now, hydrogen has its duet, so he's happy. Sulfur has its octet, so it's happy. So we're going to distribute the remaining 20 electrons on the oxygens. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have 20 electrons. The structure is finished. The octet rule has been satisfied. I had just enough electrons. All right, we have one final example that we're going to do. So let's add up our electrons. 5 for the nitrogen, 3 times 6 for the oxygens, and that -1 charge means it's gained an electron, so let's add an electron, plus 1 electron. That's going to give me 5 plus 18 plus 1. So that's going to give me a total of 24 electrons. So let's put our nitrogen down, and we're going to attach 3 oxygens to it. That's 2, 4, 6 electrons. So let's subtract 6. That's going to leave me with 18 electrons that I still need to place. So let's place our electrons on the oxygens. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I've used all 18 electrons. Now don't forget to go back and check for the octet rule. And so we are going to see that all the oxygens have their octet, but nitrogen is not very happy, y'all. He only has 6. So pick one of the oxygens, and you're going to swing a pair to the nitrogen. So I'm going to pick an oxygen, swing a pair of electrons down. So that means our final structure should have a double bond between one of the oxygens and the nitrogen, and then the others single bonds. And don't forget to put your square brackets around it because it is a polyatomic ion. Oh, that's a -1 charge, sorry. Okay, so it is a polyatomic ion. Don't forget to put your square brackets around it. And in the next lesson that you take notes on, you're going to learn about resonance structure. So this is a good place to kind of leave off in this because this is going to have a resonance structure because you had 3 exact same situations, 3 exact same atoms to borrow the electrons from for the nitrogen. So in our next lesson, it's going to pick up with resonance structures, and we'll talk about that there actually are 3 possible structures that are equivalent structures for the nitrate ion. All right, that's it for this lesson. Next lesson will be on resonance structures, and we will talk about these some more in class.